So we are recording then. So welcome to the second edition of Jfokus Brown Bag Lunch. Today we have with us the well-known Heinz Kabutz. But if there are anybody on the call that doesn't know you, maybe you can introduce yourself and take it off.
Introduce myself. All right, I can do that. Should I put screen sharing on already or not?
No,
Please do.
Not yet.
Okay.
Oh.
Yeah.
It's up to you. What do you want? Okay, I'll keep it off. So I'm Heinz. I'm originally from South Africa, and I now live on the island of Crete. So this is my beach where I normally go running in the morning, but not today because we had this massive storm coming through, and I don't know if there's a beach at the moment. There's probably a river coming down where the beach was, but I'm very interested in concurrency. In Java, I've been writing newsletters for over 20 years, actually almost 20 years. And so when this Project Loom came around, people kept on telling me, oh, you know, all this stuff's going to be so easy because Project Loom will make everything easy. And so I decided to actually start investigating what's actually going on here, because in order for us to be ready for Loom, we're going to need to do a little bit of work on our side. So, but I'm really excited to do this brown bag lunch, except that I wish I had my brown bag of lunch to eat whilst I'm talking, but that wouldn't be so nice for you. So that's for me. Also, I've got my wonderful friend John Green with me. He helps me with everything I do. He helped me set up a nice server. So we've got 500,000 virtual threads running on the one virtual machine and 500,000 running on the other virtual machine. Each has 500,000 sockets open. The reason we only have it as 500,000 is because, well, we just got bored and stopped making more. But you know, we could continue and make more and more sockets and threads. But that's actually happening. It's actually running right now, I think, if it hasn't crashed. But it's really nice, really quite amazing what you can do with it. And we had a lot of fun the last couple of weeks looking at this, and so I want to talk about it a bit. But Matthias told me that he's got we've got Alan Bateman on the call. So Alan, thanks for coming. But I'm now really nervous because, of course, Alan is one of the authors of what's going on, and I'm not. I really don't know very much except as a user, and I know concurrency, but I don't know this stuff. So it's going to be fun. Okay, so let me put off my screen sharing quickly. Not my video. Put my video off. I'll hide my video. I'll just have my screen sharing on. All right. You can see my screen. Let me see. No, not yet. Okay, put that on share. All right. So this talk should take about half an hour if all goes well. But you know, there's hopefully time for questions and comments. If you have any questions, please feel free to pop them into the chat, or just unmute yourself and ask, and we'll pick it up on that. All right. So I think I've introduced myself enough already, so I'll skip that. And yeah, questions are always welcome. So why do we need virtual threads? Right? Why do we need this? What's the point? Well, quite often what we want to do is to parallelize units of work. And if you treat all your work as simple as a single request that comes in, and it gets done with one thread, that limits the way that you can actually scale your system out. And sometimes what you want to do is to parallelize parts of a request. So you want to maybe get some of the data in parallel, get some of the database connections, get some of that data in parallel, rather than just have everything waiting on a single thread. And so I've got this little scenario. It's based on Brian Goetz's example in his book, but I've adapted it to be a bit more modern. And the idea is we've got a web page server where I'm going to try to discover the best deals out there, right? And I'm going to scan the request that comes in for all the search terms, and from that I'm going to build a whole bunch of places where I'm going to look for great deals from the partner websites, I'm also going to create some advertising links to show on my site. And then I'm going to collect all the results from the partner websites and show you this wonderful page of here's where you can get the best deals. Click here for, I was going to say flights to Crete, but it's not happening anymore. But in the olden days, we used to fly to places, and that's what we used to do. Now, you can reorder some of the steps without affecting results. You can do, for example, the advertising links at the same time as you're searching, the partner websites. There's some sort of interaction you can do, but not all of it. So in the simplest scenario, we have it simply single-threaded, and we've got the first step is to search for the scan for the search terms from the request, and that's our first step. And then the second step is we go and we create, there's a method called search on partner site on each of the search terms, which will go and then do the actual search. Then we've got the create advertising links. That's our third step. And the fourth step is we want to collate all the results. Now, I wrote this little demo just to try it out, and I gave a time to everything. So for example, the create advertising links takes 2 seconds. It's just a number. I mean, it's obviously it'd be like microseconds, but just imagine it takes a certain amount of time. And so just to give a number for all these different things, and of course, every time I send out a search on a partner site, I have to wait for them to respond. And all of this adds up to like this fictitious number of 42.5 seconds. You might hear my ducks outside. It's raining, and it was raining, and the ducks love rain, so they're really happy. Oh no, those are the chickens, not the ducks. They also love the rain. Okay, so we've got the page renderer with future. What we can do is we can sort of split it into two and have the advertising links as being one thing and the searching being another thing. So we can sort of send out the request or the partner site saying, here, just find lots and lots of different deals for us, and then we get the result back and join it up together again. Let me close the window because I'm getting annoyed by the chickens. There we go. No more chickens. They think just because they lay eggs for us every morning, they're allowed to make a big noise, but I don't agree with that sentiment. All right. Now, and so what we normally used to do is to take something like an executor service, and the reason is that in the past we used to always have the assumption that threads are expensive, right? Making a new thread is going to cost you microseconds of time, and also they're limited to how many you can make. You can make maybe a couple of thousand, maybe 10,000 threads before you get an out of memory error. So we always had this sort of worry in our mind that there's a limit as to how many we can make. And virtual threads, you can make millions of virtual threads. The real limit is going to be the amount of memory you've got, not the number of hardware threads or the number of native threads supported by your operating system. So so you're not dependent on that anymore. So here what I do is I basically make a separate task, a future, by saying execute to submit, where I'm doing all the searching with a separate thread. And it doesn't really help much because I'm still doing the actual searching one step at a time to all the different partner sites. I'm also collating the results one at a time. The only thing which I'm doing in parallel is actually the create advertising link. So time goes down to 40.5 seconds, but not much better than that. And the problem is we had this one task which was sending network messages, and the other task is the CPU doing the advertising links, and mixing different types of tasks always had a problem because some tasks would take much longer than before. And so in the past we had to be really very careful how we split the work, because for example, if you took a fork join pool and you gave it some networking to do, the threads inside the fork join pool would simply block up. with waiting for networking answers, and you wouldn't be able to scale very well. So another way one could have done it is with the completion service, where each job, each task, as soon as it's done, you end up being able to get the result in that order. So this would be the renderer, and it's a bit better because what I'm doing is I'm having a single task for each partner site. So I'm doing all the partner sites in parallel, but then again, I'm limited by how many threads I can have on my system. I can't just shoot off a basically unlimited number of searches, because I'm going to be limited in the number of native threads I can support on my virtual machine. So therefore, and I've limited this to 4 threads at the time at once, but you can imagine on a normal server, you're going to be quite limited with this. So the time goes down a bit to 22.5 seconds. And so these were sort of some of the issues we had. And so we went to completable futures. And this was Java 8. And we had this really nice technology where we could draw like an activity diagram and then convert that to actual code. So this example is not very complicated. It's basically like a Petri net. You're splitting into forking and then joining back again until you get to the final answer. But to convert it to code is a bit complicated. And I spent quite a bit of time learning how this completable future works, learning how to convert this diagram to code. And normally what I do is I convert each individual step to a single method that returns a completable future. And then afterwards, I combine all of them together. So I'm going to show you the code, but only for fun, because it just carries on and on and on. It's basically, each request becomes a method, and then I combine all the methods together. So it just carries on and on and on. So it's like 3 different pages of individual methods. What started as a relatively simple problem has become quite complicated. Now, the time has improved, and the reason it's improved is because if you look at the diagram, we actually are downloading and rendering in parallel. So we are able to download and render at the same time, or rather, individual. Oh, I got the wrong. It's not supposed to be scan for image info. John and I missed that one. It's supposed to be not download, but it's supposed to be the, what is it? The scan for search and collate was supposed to be the one that was on the right hand side. But the idea is that we're doing things in parallel, more in parallel. So we get down to 8.5 seconds. Now, all of this, if you don't know too much about concurrency, you're losing out. I've got a fantastic course, Concurrency Specialist course. You might get a Brian, oh, that's a spelling mistake. It's supposed to be brain overload, not Brian overload, all right? Brain overload. If you get a brain overload of all this concurrency stuff, come to my course. I offer it remotely to anywhere in the world. And it's the only Java concurrency course that's officially endorsed by Brian Goetz, the author of Java Concurrency in Practice. And at the moment, I don't have any material about Project Loom in there, but I can gladly do that. If anybody wants that, I'll put it in. Now, before I go into what Project Loom is and how to make this with virtual threads, just want to mention that everything that's underneath the infrastructure is the Java memory model, as we always have had. So that hasn't changed. That's still the same. So you still have the same guarantees that you've always had for making sure that memory is consistent everywhere and that you can see the correct value everywhere. It's just become a lot cheaper to make new threads. All right, so what Project Loom gives us, it gives us virtual threads where we have very, very lightweight threads. Each thread costs approximately 500 bytes, and that's because of the stack that's on there, the stack memory that's allocated. They're very fast to create, and John and I did an experiment. The first experiment didn't go so well, because what we did was we created the threads, but then and we made them. I think we made them sleep. I think we didn't. No, we parked the threads, and then we made new threads and parked them, and new threads and parked them, and we got to about I think it was 13 billion threads, I mean, and which had been started and which had all been parked. And at that point, I said, no, that sounds too good to be true. I mean, I'm sure they're great, but they're not that great. I only have 64 gigabytes of memory on my machine, and the virtual machine process was only allocated 16 gigabytes. So it's unlikely that you can make one virtual thread in 1 byte, right? So that's not going to happen. So something was going on with optimization there, which was basically throwing them away. And then we changed the test a bit so that it would remember the threads and not throw them away. And then we could allocate 32 million virtual threads in 16 gigabytes of memory. So it's a phenomenal number, you know, and you know, normally when we're working with programming, we're looking at a thread pool of maybe, I don't know, 100 threads, maybe 1,000 threads if we want, but not 32 million. You know, it's a quantity which is so big, it's really hard to imagine so many threads. Now, the way that it works is that each of the virtual threads is actually executed by a carrier thread. The carrier thread at the moment is simply coming from a fork join pool. So inside your virtual threads, or when they get scheduled, when they get to the state where they're actually running, they're running inside a thread that belongs to a fork join pool. By default, the carrier threads are daemon threads because that's what the fork join pool gives you. If you don't want them to be daemon threads, it's easy to swap out and to change it. Also, the default is that the number of threads is runtime.get runtime.available processes. That's the defaults. And this can sometimes increase temporarily due to the managed block. I'll talk about that a bit more in a moment. And also, what's also really cool is that normally when you see a piece of code from top to bottom, you know that thread is going to be busy with that, and it'll be busy with that task, and it won't, like, the thread can't be used for another task until it's done with this task. But not with Project Loom. They've got something called a continuation, which is a little bit like saving your work, right? Saving your work, like I'm busy doing a recording or something, and my wife calls me for supper, so I pause the recording, I go down, have my supper, I come back and I restart my work, and that's quite normal for us to have the ability to save work and to continue where we left off. And so this is exactly what's happening with continuations. Our work is running, we get to a wait or a sleep, and at that point they simply say, okay, well, you're done, kick you off the carrier thread and take somebody else onto that. And this happens when you're blocking on IO. It happens when you're waiting on synchronizers from the Java till concurrent package. So reentrant lock and semaphores and count on that, all of those wonderful ones are supported fully by Project Loom. Now let's go back to the single thread render. This is the original code that we had, and the reason why we even looked at using thread pools before is because we've got this limitation of how many threads we can actually make. And I had this one customer once a long time ago who created 5 threads, Java threads, whenever somebody connected to their server. And after 1,000 clients connecting, the server just fell over. And he explained the architecture to me on the phone, and I said to him, well, that's not going to work. Java allocates a native thread, and you're limited as how many you can make. And eventually they wouldn't believe me, so I went and showed it to them, and they couldn't believe it, that you can only, each Java thread is a native resource. They're limited. It's just a few thousand. So it's just not practical to create a number of native threads for every request that comes in. You can't scale that way. But if you can make 32 million threads and 16 gigabytes of memory, who cares? Just make them, make as many as you want. It really doesn't make a difference anymore. So that's sort of the philosophy here. And if you look at the original code, what we can do with virtual threads is to wrap each of the individual tasks into its own thread. So for example here, I create an advertising thread, and you can simply say thread.start virtual thread. And what that does is you invoke in the thread, in the virtual thread, this request of create advertising links. Now, this is just like the interface is like, or the interface of the class is like a normal thread. So you can't return values. If you need to do that, you need to use an executor service. But this is just calling a task. And so I also want to join it again at the end to make sure that it's done before I exit from the method. And then I do the scan for search terms, which gives you back a collection of requests. And then I've got my each of the individual search terms. I then create another virtual thread, which I then also pack into a list, so that in the end I can join each of the threads which I started. You see, the thing is, if you don't do that, you might exit before you've done all the work, and that could become a problem. So it's better to, like, unless your method returns something to allow the person to deal with unfinished work, it's better not to do it this way. And if you look at the time, it's now fully parallelized. I mean, 4.5 seconds is like 10 times faster than what we started with. So that's really great. Now we can construct virtual threads in a couple of ways, either with this very simple method, thread.start virtual thread. And by the way, you can actually download Project Loom from there's an early access. Maybe John can post the link. We can get that. You can also get the sources from GitHub and build it yourself. It's pretty easy. Just download it and build it. That's what I've done. So I've got the latest, freshest release, which is great because they're very active building and working on it. So you get the latest, freshest ones. You'll get the ones with the least bugs as well. So that's a good one to use. And then you've got the other way is to say thread.builder. So they've got a whole builder pattern, the effective Java builder, .task runnable, we pass in a runnable, .virtual.start. And if you left out the virtual, you would then have a normal thread, a native thread. So the thread build can be used for that as well. Or we can use executor services. So there we can say, for example, the executors.new virtual thread factory. That's in our shorthand. And it's, of course, an unbounded thread pool because, and it's not really a thread pool either, because you don't, the pools, normally with a pool, the object gets taken from the pool, and then when you're done, it gets returned to the pool. These get thrown away when you're done. So they get created and then simply discarded. I mean, it's only 0.5 kilobyte per virtual thread. So that just gets garbage collected and you're done. Or you can have a thread executor where you can also pass in a thread factory. If you, for example, want to have them to be non-daemon threads, you can do it that way. Or some other characteristics, you can do it that way. What's also really cool, and this is super cool, it's not just cool, it's like super cool, is that executor service is now auto-closable. And this means it's got a close method. And the close method has calls shutdown, and then afterwards calls await termination. It doesn't call shutdown now. So for example, if you want to stop all threads which are waiting on an IO stream, for example, on input stream from or socket input stream, then close won't do anything because it's going to just wait for them to finish. Once they're finished, then it will close, but not before they're finished. But what you can do with virtual threads, is what you can't do with native threads, is you can interrupt threads which are waiting on a socket, and it will come back with an IO exception, close by interrupt. So this is something new. They haven't changed the old behavior. So if you have normal threads, and the normal threads are waiting on input streams from a socket, and you interrupt those, they still won't do anything. It just won't return. But virtual threads return with an interrupted exception, or not, sorry, an IO exception with the message closed by interrupt, which is really great because that's something which has been missing from Java for the last 25 years, I would guess. So at long last, we've got that. Now, the fact that it's also closable brings us to another way that we can write this code, which is with something called structured concurrency. And that is, I've got, like for my request, I'm going to create a new pool, just make a new pool. It costs nothing to make a new pool. So I make a new pool of my virtual thread executor. I submit my create advertising links, and I submit another task, which is the one where we search and collate all of the results from our partner sites. And the search and collate pool is now another pool I make. And this is a try with resource. So I'm only going to exit from here once all of these jobs are done and the pool is closed. And so when you do this sort of structured concurrency, you need to be careful not to submit jobs to the main pool from inside other tasks, because remember that if you look at the main at the submitting thread, the submitting thread will start the main pool, will do the submissions, and then will immediately call close, which will shut down the pool and then wait for it to shut down. So if inside my task I then try to submit again to the same pool, I'll get a rejected execution exception because the pool's been shut down already. So that's the mistake I made when I first tried this. I tried to have the actual collation being done also inside the main pool, and then I got all these exceptions. Said, what's going on? But of course, it makes perfect sense because you want to make just another pool. It costs almost nothing to make a new pool, so let's make a new pool. All right. So this is some really cool technology, and I'm actually, seriously tempted to to run my server off it, but I'm just a bit scared because that's my bread and butter. That's where I make my money. So I don't want that to just disappear, because we have had in early releases of Project Loom, we had a few crashes, and with this crazy idea we had of starting like hundreds of thousands of sockets. And I'll show it to you. It's running at the moment, actually. So so here's our server, and our server has got 500,000 connections from our client machine. Our client, we did it on the same machine because otherwise the networking would just be too slow. And what the client is doing, the clients are sending messages, just text messages, and then they're being sort of uppercased, or the case is being reversed and sent back again. And every 5,000 of these we actually print to the screen, and you can see it's pretty busy outputting stuff to the screen. So this is on our server. And the only thing we're really seeing is there's some garbage collection going on, because there are 500,000 of these things in memory. So it shouldn't be surprising. We in the early version of Loom, we actually had it crashing with the G1 processor collector, but it worked fine with the parallel collector. So, but this is now running with G1 with the latest version of Project Loom. So it seems to work quite nicely, actually. And what's quite funny, if you do a thread dump, how do you do that now? How do you do the thread dump? Let's do a thread dump here. So we'll do a JStack, a JPS. So if you do a thread dump on the server, for example, now remember this has got 500,000 threads.
Your picture is a little bit in the way for that.
So we are just watching your face. So perfect. Thank you.
500,000 threads, right? But it doesn't show all the virtual threads. It only shows the carrier threads. The carrier threads are these fork join pool, one worker one. So that's what you're actually seeing. Okay. and it shows you where they currently are. They're all busy waiting for work. They're basically not busy because my 500,000 threads are sending a message, then waiting a second, getting a response, waiting a second, sending one back. So it's just backwards and forwards, ping pong, like that. Also, if you take JMap minus histo and you look at what the memory is doing, you can see that, let me just head minus 20. You can see that the biggest cost are byte arrays. They're like 1 million byte arrays, which I believe have to do with the underlying socket infrastructure. Then you've got the stack chunks. That's for each of the threads. Not sure why we only have 349,000. Maybe some of them died, I don't know. But I'm not quite sure why. And then, like, but I mean, the actual memory being used is minimal considering what we're doing. So that's really quite cool. And it's busy running now. It's just, this is, oh, you can see 500,000. Ah, right. So there are 500,000 virtual threads. Oh, this is 3.5 million, not 349,000. So there are more stack chunks than I thought. Right, so it's all working. That's on the server, and my clients represent 500,000 clients. So it's not really fair to look at that because you'd have to divide it by 500,000. But yeah, there you go. It's busy running right now. All right, a few things I want to mention. There's a concept called a managed blocker. This has been around since Java 7. And the idea is the following, that when you've got a fork join pool, if one of the threads, if one of the tasks blocks for a long time, for example, you're doing a synchronized wait, or you're doing a lock.lock, or maybe you're opening a socket and reading from a socket. In those cases, you could make a managed blocker, and the managed blocker would enable you to possibly create more threads in order to keep the parallelism high for your fork join pool. So by default, the number of threads is the number of hardware threads in your system. So my machine's got 16 hardware threads, so it's got 16 threads in there. But that's the desired parallelism, and the managed block allows you to make more. In the first version of where this arrived in Java 7, only the phaser class implemented managed blocker. And then Java 8, they added computable future. Java 9, they added process and submissions publisher. And then in Java 14, they actually added that to the abstract queued synchronizer. Now, which means if you've got a task, any task, it could be a parallel stream task that happens to lock on a reentrant lock, and maybe it goes to condition.await and it just suspends the thread. The fork join pool can go and create more threads to keep the parallelism high. Okay, and this is true for reentrant lock, reentrant read write lock, count on latch, and semaphore. All of these are because they all use abstract queued synchronizer, they all automatically get thrown in for free, the fact that they're managed blockers. All right, and then in Project Loom, what they've done is they've pulled in some of the new changes coming from JSR 166, which is the Java util concurrent API. And there they've also added this to link transfer queue, to synchronous queue, and to selector impl. So even selector impl is now going to be managed blocker going forward. So this is really, really good news, because it means that we actually can write code which blocks, and if it blocks, it's not the end of the world. It'll just create another native thread to pick up the slack. And when I say that the fork join pool creates additional threads, it's not making additional virtual threads, it makes additional native threads. That's what it's making. So of course you could run out of threads in theory, but I don't think it will let you. I think it will only go up to a certain limit, if I'm not mistaken. Now we need to check our code base, because if we've got any place where we've got native method calls that are blocking. In other words, we are maybe synchronizing around the native method call, and it takes a while to answer, to come back. It takes non-trivial time to return. We need to wrap our code with the managed blocker. I'm not going to show you how to do it. Have a look, and you'll find examples in the JDK. Another thing they did to make the JDK ready for Project Loom was to completely rewrite the Java I/O. They used to have something called plain socket impl, and they've replaced it with the NIO socket impl. That was JEP 353. And one of the things they did is they changed places where they use synchronized to using reentrant lock. So synchronized, you can see synchronized state lock, and they've got some code inside, and they've changed it to say state lock and state lock.unlock using a reentrant lock. And why would they do that? Well, why? Well, unfortunately, well, here's the thing. Synchronized is generally is easier to get right than reentrant lock. And I've been saying for the last 13 years since I wrote my concurrency course, or the predecessor to the concurrency course, I've been saying for a long time, prefer synchronized over reentrant lock because it's easier to get the idioms right. Plus, in many cases, synchronized performance will be better. If it's an uncontended lock, synchronized is faster than reentrant lock. One of the reasons is that biased locking assigns a lock to the first thread that gets it, and then gives it preferential treatment. And so very often you'll get almost the same performance with uncontended synchronized code as with unsynchronized code. So that's really great optimization. Also, debugging synchronized code is much easier. You've got better tools for finding contention, for example. When you have a synchronized thread waiting on synchronized, it goes into the blocked state. But if you, if you're looking for contention, you just look for blocked, and you see, I found my contention. But reentrant lock goes into the waiting state. And the waiting state, it's not that obvious where your contention is. So synchronized is easier to debug. It's in some cases faster, and it's easier to write. So I've been saying for a long time, use synchronized rather than reentrant lock. However, not yet. However is coming in a moment. Also in the JDK, the classes started moving back to synchronized from reentrant lock. So let me quickly have a cough. All right. So in Java, when Java 5 came out, we had ConcurrentHashMap, which used reentrant lock. Also, copy and write editors also used that. But then in Java 8, they changed ConcurrentHashMap to use synchronize internally for its locking. And copy and write editors started using synchronize in Java 9. But the problem is with synchronize that it's not really that compatible with Loom. Now they do say in their what's next that they hopefully will include it one day, but I would not count on it happening too soon because it's really complicated to do. And in my code, I'm not going to wait for them to do that. So in other words, and the problem is if you wait, for example, on synchronized, you're going to stall the underlying carrier thread. For example, here, I've got an object monitor equals new object, and I go from 0 up to available processes, and I start virtual thread, synchronize monitor, try monitor.wait. So all the threads go into the waiting state. They're waiting on the monitor. And if you do a thread dump, and inside your thread dump, you see all these carrier threads from the fork join pool, which are on the native state object.wait, you've got a problem, right? You've got a problem. And you can see this one will never have any output because all the threads, which are the carrier threads, are now used up, blocked. They're not blocked, they're waiting for the signal, which is never going to come. And so it's no longer usable. Everything will just stop, right? And You've got a similar problem with infinite loops. If you, now of course I could interrupt those threads, that would work, but I can't stop the threads. So if I've got an infinite loop, it's actually even worse, because here it will never return and there's no way of stopping it. At least with native threads, you have the option, even though it's deprecated, of calling stop. That's not an option with virtual threads anymore. All right, so we must be careful of that. And because of that, we need to change our code, migrate our code from synchronized to reentered lock, or even better, to stamped lock. Again, I'm not going to go into the details of how to do that, how to do stamped lock, but there are some great idioms you can use for that. A lot more complicated, but in many cases, much, much faster. And I actually wrote about stamped lock a few months ago in my newsletter, and I wrote the newsletter, and the same day, somebody sent me a check-in that somebody had done on the same day, where they replaced some file IO code, I think it was, with the stamped locking, and they had a huge improvement in performance. So just an amazing coincidence. So yeah, the problem is these idioms are more difficult, but your performance can, in many cases, be much better and more compatible with virtual threads. One of the things they did in Java 15 is to turn off biased locking. I understand why. And the reason is that it's really complicated. It uses a bunch of bits on the object headers to, they actually use the same bits as the identity hash code. And so, but the whole thing is really complicated. And it's difficult to justify, because most of the time it won't make a difference having it on or off. Most of the time you will not find a very big difference. The only time that you find it being it helping you is if you have a lot of unnecessary synchronized. If you've got lots of places where you've got synchronized, you didn't actually need it in the first place, then biased locking will optimize it away for you. It's like auto-boxing. Auto-boxing is not really supposed to make your system faster. In a perfect world, it won't make a difference. Perfect world, it'll be the same speed as without auto-boxing. But if you are creating lots of unnecessary objects, auto-boxing will make it much faster. So you might find when you go to Java 15 that your system runs slower. You can't, okay, I can't say you can't, but I haven't thought of a good way to detect places where uncontended locks are making us slower. It's easy to find contended locks and find those, because you do make a thread dump and you see all these blocked states of threads, and you know exactly where it's slow. But for uncontended locks, you don't see any states because they're all runnable. Everything's fine. But it is being slowed down because it always has to get the lock and get the lock over and over again. So it's something which is very hard to find. The only way that you can try it out is to measure the performance of your system, compare to Java 14. If there's a difference, turn on biased locking in Java 15 and see if it makes a big difference. And if it does, please file a bug report or something so that people will know that actually there's been a regression there. Another thing which happens is that in the past we had thread locals, which we use unfortunately quite a lot, and they're very costly to support. It needs to make a weak reference to support it and so on. And virtual threads are not reused. So thread locals don't make that much sense. And there's a couple of slides, Elena, then we'll stop. So scoped, so instead of using thread locals, you can use scope variables and immutable objects, and you can also disable them explicitly for virtual threads. The last thing is the disconnect between the state machines. You've got the Java Lang threads, which are 6 threads, very simple. The Java Lang virtual thread has 11 states. Right now, they sort of hide that from you. The state machines, this is a normal thread state machine. It's fairly simple. And I spent about 2 or 3 days drawing up this thing, right? I put in my name, so if anybody copies and pastes it, you know, this took me a lot of work to get this one right. to see what actually is going on with the virtual threads. And but if you say get state, you're also going to get, you're not going to get the actual virtual thread states. It's going to give you back something slightly different. This is the last thing, which is the cost of old IO streams. And that is that the benefit of virtual threads is that you can use, you know, input streams and print streams and buffered readers. It's fantastic. And John and I did that, and we couldn't understand why the clients were using like 50 times as much memory as the server, or 20 times the memory as the server. We couldn't understand that. And then we did a JMap, and we discovered that actually what was the biggest was the print stream. So the print stream, each time you make a print stream, it's 25 kilobytes, just, or 24 kilobytes, 25064 bytes, just for the print stream, right? The buffered output stream and input stream, 8K, buffered readers and writers are 16K each, because it's an 8K char array. So we did this just before the talk. We made this little table to see how much everything would take. So it's be very careful with these, because they use a lot more memory than you might realize. It's okay if you've got 100 buffered readers, it really doesn't make a difference. But if you've got 500,000 buffered readers, all of a sudden it's you've got a serious amount of memory that you've used up. So 16 gigabytes is just is just your buffered readers, or 1.6 gigabytes, a lot. So I've come to the end of my talk. It's the first time I'm giving this talk, so love to hear your comments and your questions.
Perfect. Thank you very much. Great talk. Before we are taking questions, I will stop recording and ask all co-hosts to stop recording as well.